So let's recall where we were last time. So last time we were using the following definition. So we started with an object M in the derived category of light condensed abelian groups, and it was called solid if it had this property that, well, so the internal hum from this object Z, Z brackets Q hat mod n times Q hat minus 1, where n is an integer. So the Z brackets Q hat was the free, it was sort of the free object on a null sequence. Then our hum from there into n should be 0. And we said that D of Z hat was the subcategory of solid objects in D of Z. Oh, okay. So maybe I should just write. So also equivalently, right? So equivalently, I mean, if you just take our internal R hum from D of Z hat into n, you get the space of null sequences in n. And so equivalently, the statement is that I guess 1 minus n times the shift operator as a map from null sequences in m to null sequences n in m is an equivalence. So this was the definition of solidity. And basically, as a consequence of this internal compact projectivity of Z brackets hat, that implied this fact that it's an analytic thing. But so today I wanted to explain so the following theorem, or at least some of it. Okay, so one is, okay, so maybe before I formulate the theorem, so any object, so again by sort of well, by adjoint counter theorem. So right, so for all M and D of Z, well, we can form its solidification. Which is a universal solid thing that it maps to. And okay, so then one has the following theorem. Okay, so the solidification here exists for abstract reasons, but then the theorem is that it can be computed very quickly. So if S is a light profinite set, then Z brackets S solid is equal to the inverse limit of okay. So if so, I should say S is a light profinite set. So that means S is the limit of some finite sets S of I. So S is a sequential limit because it's a light profinite set. It's a sequential limit of finite sets. And then the statement is Z brackets S solid is the inverse limit of Z brackets S phi. And abstractly, if S is not finite, so if S is finite, this is just Z brackets S. And abstractly, this is so if cardinality of S is infinity, this is the product over n of, and this product is computed in light solid abelian. Okay, so this was the theorem from last time. So yeah, so I guess I wanted to say something about the proof of this theorem. Okay, so the proof of this theorem. So okay, so let me also explain. Like, so what's a consequence of this theorem? So I guess one has to, use this and also think about what maps between, products of Z are, which I guess is going to be implied by this. And so let me just see. So corollary. So corollary is that D of Z hat is the same thing as well. Okay, so let me just say is compactly generated. Compactly generated by a countable product. And the endomorphisms of this object are sort of the endomorphisms that you expect, and that's this description of D of Z solid as a modular. So I wanted to explain the proof of at least some of this theorem. So I wanted to explain that okay, so Well, I wanted to essentially explain the proof if S is the profinite set n bar. So proof when S is equal to n bar. So in this case, right. So in this case, it's equivalent to the statement that if you take this object Z brackets and solidify, it's the same thing as Z double brackets. So this kind of makes sense. We have an element which is topologically composed. To make it solidified, you should be able to sort of form power series, integer coefficient power series in that element. But this requires a couple of steps to fully. So step one is the following. So if you take the real numbers, so the real numbers, if you think about that as a light condensed stimulating group, then or light condensed ring, in fact, then its solidification is equal to 1. So the real numbers have zero solidification. And I think this is an important ingredient both in the light approach, the current light approach, as well as in the earlier, well, not necessarily light approach. Okay, so let me explain the proof. So the proof is that okay, so right. So the proof is that there's a right. So there's the element 1/2 in the real numbers, which has the property that it's topologically nilpotent. But 2 times 1/2 minus 1 is 3. So the proof is that R is a module over Z adjoint Q hat mod 2 times Q hat minus 1 via Q hat mapping to 1. Well, if you like, this is an algebra, so Z brackets Q hat is a commutative algebra, and we can map it to the real numbers. Well, we just have to send by construction, we have to send Q hat to something which is topologically nilpotent. So we send it to 1/2. So it's a module of this thing. But the whole point of solidity is that any module over this ring has to get solidified to 0. So these are precisely the objects. So more precisely, solidification, it's a localization away from the tensor ideal. So solidification is a localization of the tensor ideal generated by this object Z brackets Q hat mod n times Q hat minus 1. So by construction, well, right, so this object Z brackets Q hat mod Q hat minus 1 solidified equals 0, and that implies R solidified. Okay, so right. So this is so this step, yeah, so maybe a comment is that this used the fact that you put place 1 by 2, but in fact it's with something more elaborate argument. You can just oppose this for any of this 1. But in any case, when we want to talk about solidity over a ring that's not the integers, we'll want to impose this type of condition not only for with more general coefficients. Okay, so this is step 1. All right. Okay, so step 2. So again, our goal is to show that Z brackets Q hat solidified is Z double brackets Q. So let me just explain, maybe I should explain this first. Let me explain sort of naively what the idea is. So if you have a power series, so okay, so again, I mean sort of an aside. So given a power series, So given a power series, sum of a sub n times, sorry, q to the n, for n greater than or equal to 0, a sub n in z. So this is living in z double brackets q. We'd like to see that it belongs to z brackets q hat solidifying. So we'd like to realize it in z brackets q hat solidifying. Now the whole point of solidity is that whenever you have a sequence that converges to 0, you're supposed to be able to sum it. So you're supposed to be able to think that this is the sum of a sub n, q sub n in the solid sense. So a sub n, the individual terms, a sub n times q to the n, belong to z brackets q hat. But the problem is they don't converge to 0. So here are the individual terms. So individual terms, a sub n times q to the n. So they belong to this sub-object z brackets q hat. But the problem, so we'd like to say that we can sum them together in the solidification, but the problem is that they don't converge to 0 unless the a sub n's are uniformly bound. So, but don't converge to 0 unless the a sub n's are bounded. So that's actually why you need this step 1. So I'm sorry, I said this a little bit out of order. The idea is that, well, so the idea is again that you want to write this as the sum of these individual terms, which belong to the subring or to the sub-object z brackets hat. But you have to work a little bit more because to work a little bit more if the a sub n's are not uniform. Okay, so step 2 is going to be to show that the map from z brackets hat to not all of z double brackets q, but z double brackets q bounded induces an isomorphism on solidification. So step 2 is to, instead of working with all power series, let's work with power series where the coefficients are uniformly bounded. And then we want that this map is an isomorphism on solidifications. And the idea is that if the a sub n's are uniformly bounded, then these terms a sub n q to the n, they do converge to 0 in z brackets q hat. So we should be able to point this. So the idea of step 2 is to make this informal argument, is to take this informal argument. Yeah. Just okay, so you're saying so sure. That sounds okay. So that I think yes, I guess I agree with you. But I guess we also want to say this sort of diagrammatically. So we want to write this as morphism, like right. So we want to show that yeah, okay, so I agree. So I think your argument will show that it's gonna imply that this sort of okay, yeah, thanks. Okay, well, anyway, we need to show that this map is an isomorphism on derived solidification. Okay, but so yeah, so I guess I'm not sure how to do that, like splitting a sub n into n terms. I'm not sure how to do that diagrammatically. Okay, but we can okay. So okay, so the idea is that right. So again, both of these are going to be in profinite. So both sides are in profinite. So if we look at z double brackets q bounded, so right, so we already saw in the previous lecture. So z brackets q hat is it's the union. You take the union where there's a total L1 bound on the polynomial. And okay, so we know that this is sort of in profinite, and then z double brackets q bounded. I mean, it's the union of all power series, C double brackets Q, all coefficients are of absolute value less than. So this is profinite.
And from one of this, it's a property of solid set.
Yes. Maybe I should say
Because you have the group structure that is solid sets.
yes.
They are.
So these are maybe more, yeah, so more precisely, I should say that these are sequences. We can think of both of these as given by like sequences of profinite sets under closed embedding, under inclusions. And yeah, so I guess the point is that these are like we're considering these in the object of in the category of condensed abelian groups, but they're really more or less classical objects in that they're basically sequences of profinite sets, and so you can work with them as such. Okay, so in particular, you can define maps between them by just thinking about continuous maps between profinite sets. Okay, so I think the idea of this argument is sort of to make this kind of intuition into a precise diagrammatic diagrammatic statement. Okay. Okay, so the strategy is that we're going to define a sequence. We're going to define a sequence of, well, let's say a null sequence of endomorphism. So we have this inclusion of sort of light condensed abelian groups, which are in fact more or less classical topological abelian groups. And okay, so the strategy is that so for each I, we can consider the endomorphism. Let's say I greater than or equal to I from C double brackets Q bounded to C double brackets Q bounded, which truncates the power series in coefficients greater. Well, it takes so extend the power series sum of a sub n n for n greater than or equal to 0. It sends that to the sum of a sub n to the n for n greater than or equal to 0. So it's a sort of
Is it the product sum or just the letter pi?
that is just a letter pi. So we're going to project in this way. We're just going to ignore all the coefficients of q to the something less than I, q to the n for n less than. Okay, so this is an endomorphism. This is an endomorphism. So now we're ignoring the ring structure. We're just considering the condensed abelian structure. So this is a map of okay. So this is great. I mean, it's a map of like in profinite sets. It's definitely continuous, and so this is an endomorphism. So this is an endomorphism. Say light. Well, I guess I've been dropping the word light, but it's an endomorphism. Adds a light condensed abelian group. Okay, and it preserves the subobject Z brackets Q. So it preserves C brackets Q hat sitting inside C double brackets Q hat. And I guess I'm sorting C double brackets Q got. So it preserves the polynomials. Again, these are really just operations in sort of the classical world of like in the sequences of profinite in systems of profinite sets. Okay. So right. So this gives a sequence of endomorphisms, but actually it's a sequence of endomorphisms. It's converging to 0, right? So these are converging to 0 in the profinite topology. The profinite topology again, if you restrict the bound to be outmost n, if you put a uniform bound on the coefficients, then these are the product topologies, and so these maps are tending to zero in that those response. So first. Okay, so the pi greater than or equal to I form a null sequence of endomorphisms. So I don't know, I guess they give a map from n bar to endomorphisms of z double brackets q bounded. Both this and to end somehow compatible. I guess we could say endomorphisms of
Not
additive endomorphisms.
because just yes.
And they also preserve the count. And the feature is that so it's sending infinity to 0, and it's sending 0 to the ideal. Okay. So now basically the key feature is that so this gives you a sequence of endomorphisms which is converging to 0 starting from the ideal. Now, guess the observation is that if you take so I don't know, right? So yeah, I guess if you take this pi, I guess I should give this a name, so like pi greater than or equal to star. If you compose this with the shift operator -1, if you compose this with the 1 minus the shift operator, so in other words, if you consider the sequence, pi greater than or equal to I minus pi greater than or equal to I plus 1, it actually is it's gonna carry the z double brackets q bounded into z brackets q hat. So this is going to induce a null sequence of endomorphisms of z double brackets q bounded and z brackets q hat. But this actually carries z double brackets q bounded into z brackets q. So in particular, if you think about the induced null sequence of the quotient, then the claim is that so in particular, that's because pi greater than or equal to I minus pi greater than or equal to I plus 1 is just like a sub I q to the I, so it's a polynomial rather than a power sequence. So so I guess the observation is that pi greater than or equal to star. Well, first of all, it induces a null sequence. So it induces it's a null sequence of endomorphisms. Of z double brackets q bounded brackets q hat, and it has the property that on this quotient pi greater than or equal to star composed with 1 minus the shift operator is 0. So again, I guess there's something one has to be right. So one has to be a little bit careful with. So the statement is that this sort of, well, so I guess ways, one doesn't have to be too careful, given that these are actually just profinite in profinite sets. So you can sort of check things pointwise. So this assertion is really a pointwise assertion. So if you take this null sequence of endomorphisms, when you compose it with 1 minus the shift operator, it carries this larger object into the smaller object, which is to say that it induces a zero endomorphism of the coordinate. Okay, so the conclusion, so the conclusion is that on this function, z double brackets u bounded, mod z brackets hat, we have the induced null sequence of endomorphisms. So that's right. So null sequence of endomorphisms. So maybe I should get this name. With the property that 1 is that pi greater than or equal to 0 is still the identity, and 2 is that pi greater than or equal to 1 minus the shift operator is equal to 0. But this, I think this is already enough to tell you that the solidification is 0. So this solidification so right, so just sort of abstractly again, the idea is that this, if you these identities, they're in null sequences of endomorphisms of M, but that also means that you get the same identity in null sequences of endomorphisms of M solid. And on M solid, the point is that 1 minus the shift operator is an isomorphism. So if something is annihilated by 1 minus the shift operator, it's just 0, and then you get that the identity is 0. So this is because 1 minus the shift operator is an isomorphism on, I guess, null sequences of endomorphisms of M. Okay. So in particular, you have a null sequence that's in the kernel of 1 minus the shift operator that forces to be 0, but then from this you get the identity is 0 on M. Okay. So that's this diagrammatic argument which okay, so that's the proof that z brackets q hat and z double brackets q bounded have the same solidification. But then you have to go from z double brackets q bounded to all of z double brackets. Anyway, I just wanted to say again that like I think all of these diagrams, it's a little bit confusing because you have these. I mean, one has to be a little bit careful to think about null sequences and endomorphisms and so forth. But all the diagrams are really happening in this quasi-separated set. So that's not so far. It's like, yeah. Okay, so step 3. Okay, so then one has the claim that C double brackets Q bounded to Z double brackets Q is an iso on solidification. Right. So this is where we're going to need step one. So the proof is that right. So we want this map to be an isomorphism on solidifications, and the idea is that you can extend this to a pullback. So extend to a pullback, I guess a derived pullback, where we replace D double brackets Q bounded with R double brackets Q bounded. So again, this is an infinite object. So for each n, you take all power series of the real numbers where all the coefficients have absolute value at least n. So it's a countable product of minus n comma n, and this maps to just all of our double brackets. Okay, so the claim is that this is well, I guess a bicartesian square in light condensed stability groups. Pull back and push out, or a Cartesian square in the derived. Yeah, so right, so if you have a power series of real coefficients, you could take the floor function or something of all the coefficients, and then you write it as a sum of something in here and something in here. So that's why. So these two maps are joint. Well, if you take so this is generated by these two, and the intersection of them is exactly this. So this gives you a bicartesian square in light condensed between groups, and now these two are R modules, so their solidifications are. So since the bottom, well, since solidification is an exact functor and it annihilates all R modules, so the bottom consists of terms are R modules. They're annihilated, they have zero solidification. Which proves this one. So this is where the real numbers get used.
So just a moment. So have we already it's a bicartesians? We are confused. So where did we use the result of?
So we didn't use step two. Sorry. So step three. I guess step three is that this map is an isomorphism, and then if you combine step two and step three, then
how did we use numbers for the system to replace R? That's like with the population
well, I don't.
So real numbers appeared step one.
Yes.
I think so. What did we use about real numbers? Did we use that? So we use that is 1/2.
Yes.
Maybe we also that. After multiplying half, let's say that non-topology. So I don't think we use much about numbers.
Yes.
So can you replace R by Q or by C? 1/2.
So let me just.
So you see, the strange thing is that the theorem that we're proving is nothing like numbers, nothing which would predict that numbers.
Yes. So okay. So the question is, can we use the Z join 1/2 with the topology that you get from the real numbers? To run this on. So with topology from R Okay, so. Right, so you're saying that,
You can leave this as an axis.
okay. Okay, thank you for this question. Yeah. So let me just write this in the board. So question one place. Argument. Joy and a half. Oh. Yes, I was a little bit scared about considering some of these very non-complete things, but I guess not what to say.
Not complete.
Well, I guess you're saying that Z of well, we could look at we could totally make this into a light condensed set, and well, I guess the question is just to well, if we can make this, I guess it's because Z brackets Q hat should run up into this. Yeah, thank you for the comment.
Okay, so this was step 3. I now go saying that we have to combine the source.
Okay, so step. Sorry, so we still need the Archimedean topology, but we don't need the real numbers. Okay, so that's a good point. So okay, so combine step 2 and step 3. To get the brackets you have solidifies it's the double brackets. So, yes,
actually, it's not, well, and it's not locally compliant thing. I mean, you can consider it as part of real numbers. No, it's not locally compliant, and I just don't see how we make it. That's
well, could we say that it's I mean, could we say that it's a subset of the real numbers? But so a map from S, like the map from a profinite set, if it's the adjoint 1/2 is mapped from S into the real numbers whose images and the adjoint.
but this means that would it not be that it's actually discrete? So you have, if you have, I mean, if
Well, in principle, there are conversions. There are sequences in the F1 which converge with points. You cannot. Well, for instance, and bar can be mapped to step 1. But I don't know whether the topology would be.
I guess it will not be in profinite. Will not be or at least it will not be like a sequential like expanding set of profinite sequence of expanding. But on the other hand, you do have some convergent sequences. I mean, it's also not discrete. And I guess you should have a map from Z brackets to hat to here sending yeah.
Okay, so Sasha expressed dependence doubt about like so maybe so there is still an axis. Okay. But anyway, with
Well, thank you for that. Okay, maybe I should just yes.
Like M lots of like solid, then like that it's also.
Yes. So
There's general, but I only have the confidence.
yes, so this is part of this analytic ring. So in an analytic ring, when you take Rhom from anything into just if it's complete, then it's also complete. And I guess that's because you're localizing away from a tensor ideal. So an object, yeah, it's because you define something to be solid if and only if there's what's a condition on the internal Rhom. So okay, so maybe let me just say that so this right, so this is the proof of this fact. And so more generally there's this fact for any finite set. And well, as far as right, so I think the key case is actually something that's where the finite set is Z2, quadratic integers. And I think the idea is actually just sort of approximated by this case, and to make sort of similar types of arguments, well, some similar types of arguments, maybe instead of sort of truncating to Z mod to the n. And but maybe since so maybe let me not okay, so let me just so sort of conclusion. So the conclusion is that this PFC solid is generated by this countable product of populous the integers, and also that the tensor product behaves the way that you want. So this is a solid tensor product. So basically, so I can say compactly, and the solid tensor product of countable product of copies of C with a countable product of copies of Z is again the countable product of n cross n of copies of Z. Okay, so okay, so I think an earlier from an earlier discussion with a more sort of invariant way of saying this is that so D of C solid is the category of functors, let's say additive. Oh, okay, so it's the category, affinity category, functors which are finitely additive. From countable free abelian groups sorry, let me just say this in a little let me just say this at the level of the harm. So just solid abelian groups. Into abelian groups. So that's well, okay, so here you have a countable direction of copies of C. It's corresponding to this object. And the tensor product is a Bay convolution. So right, so this is a general function when you have like functors. So it's a well, okay, so it's it's a general tensor product that you'll have on functors out of the symmetric category. So it's basically its left-hand extension along the tensor product. Maybe let me not say more.
But it's a standard.
Yes.
Yes. possibility.
So I meant that this is more of an aside, just to sort of indicate that one can define the notion of light condensed group, but also the tensor product in sort of a purely synthetic fashion.
So we're saying that countable that form. Yes. And
I'm sorry,
yes, I just think it's an option because it's countable. And therefore, by your thought, such active functors also form as a category, and this your thought because of the name is called vector.
Okay, so again, right, so the compact generator is, well, I guess another way of saying it is the compact generator is Z double brackets T, power series ring. So if you give that the T-adic topology, the inverse limit of this Monte, yeah, this is a compact generator of solid abelian groups, and a Z double brackets T tensor solid with Z double brackets 2 is a power series ring into the Z double brackets T common. So yeah, so maybe I should say something about that, about where the solid tensor product is coming from. I mean, this is because if you, well, sort of the construction is at Z brackets S, where S is profinite. So this is really coming from what's in Z brackets S. So solid tensor Z brackets T, solid. Then you solidify again. This is Z brackets S cross T. So it's using, this is really, this fact here is really a consequence of the description of Z brackets any profinite set solidified as this inverse. So I just wanted to do a couple of examples. So the example is that if you take the ZP and then tensor, or take solid tensor with ZL, this is either equal to ZP if P equals L or 0 for P not equal. So the solid tensor product of ZP and ZL is sort of what you would expect for sort of a completed topological tensor.
Derived set.
Yes, this is all, everything is derived here. Yes. And the reason, well, use the above and write ZP as the Z double brackets, right, so Z double brackets T mod okay. So in particular, ZP is an idempotent object in, well, so conclusion is that actually ZP is idempotent, an idempotent algebra in, let's say, D of Z sub. So actually, probably this will be the most the cases by relevant for the upcoming series of talks will be sort of over ZP. So I wanted to say some things about ZP solid in particular.
Are there so that you can take something like this. of times L, or maybe I take arbitrary set of primes.
Well, sorry, ZP tensor ZL will be
No,
zero.
no, tensor, but
Leaving the product.
continuum.
Sure, yes.
Yes, and probably more generally would take any in infinite connection primes.
I think so.
Take
Yes.
something, for instance, we had this hat.
Yes. Yes.
But are there other important?
Well, I mean, I guess you also have things like Z adjoint 1/n. That's still, and then you have QP, for example. So QP is like,
So
so QP is idempotent because you start with something idempotent and then it repeats. So
is there a description of all important?
So I don't know. I think that's a great question. So in general, I think in this, so yeah, so sort of one sort of observation side that they make, and so both in this setting and also in the setting over the complex numbers, is that you have way more idempotent algebras. You have a lot more idempotent algebras in these categories, in these sort of larger categories than you do sort of in the more classical algebraic categories.
So you mentioned some examples.
Yeah, so I mean, right, so in the setting, something like the Tate algebra becomes an idempotent algebra.
What do you mean by its
Say over a Planoff ring. Say the ring of functions on the closed well, like the functions converging onto this.
functions converging on the things?
So yeah, so let me say it this way. So right, so there's a lot more idempotent algebras, and an example is the algebra, let's say QP brackets T. So all power series some AI T of the I 0, where A sub I is 0. So this is idempotent, say, over the polynomial. This is definitely not algebraically, so already like ZP is not idempotent as an algebra over Z. But in the solid category, yeah. So of course the difference is that you're actually putting you're taking into account the topology on. Okay, so I guess I wanted to say something about so I wanted to say something about solidism, because in a sense where a lot would be happening. So okay, so okay, so let's write oh, so remark is that so see that we have Z solid as an analytic ring, and we can also define ZP solid as an analytic ring. And well, by definition, it's so an analytic ring. Well, first you give it a condensed ring, so that's going to be ZP, and then you give a class of complete modules, and these are going to be well, these are just going to be those modules which are solid as underlying objects of D. So define sure. Okay, so define analytic ring. So here D is solid. Well, it's sort of an analytic ring. There's sort of not really any new information. It's just putting modules in D of Z solid over Z. So this is modules in D of Z solid over the item group algebra. And in this case, so it's also so because D of Z solid has a compact generator, namely Z double brackets T. This is also going to have a compact generator, and it's going to be ZP double brackets T. So this is compactly generated. Generated by ZP tensor, but again solid tensor, over this countable product or related as a power series ring. So Z brackets T. And again, using the description of CP over there, using the description of the solid tensor product and power series, this is ZP. Well, I don't know. Okay, so this is as a, sorry, I'm not thinking about the ring structure, so this is just as a ZP. So it's sort of, so the compact generators are pro P, are, so compact generators, compact are, let's say, for free pro P of Euler curves. Yes. I guess that's just another way of saying basically products of, oh, sorry. Well, with this countable, that's basically another way of saying that the objects are basically countable and countable complexes. So these are the combinations. So, there was a description. There was a following. Or well, that's for safety. That's just now. What would be a similar answer for CP? Can we say that these are models over screen? Maybe filters from negative functions. Okay, so because this would allow it's for some purposes it's sure. So yeah, I guess I should say, so, right, so again, you have a compact generator, which is a countable product of copies of ZP. So you could let R sub P to be the ring of endomorphisms of a countable product of copies of P. And so this here we could think about this in purely classical terms. Namely, this is a profinite group, and we could look at all continuous endomorphisms. And okay, so yeah, so we're just looking at all continuous endomorphisms of this of this profinite group, and then D of the solid. Again, because we have a complex generator, is the classical derived category of R sub. And so that's because this object is a compact generator, and its endomorphisms in this like solid the same as just continuous endomorphisms as a profinite ability. So this is yeah, synthetic description of TFC solid, and right. So I guess we can also describe the tensor. Should also be able to describe the tensor product. So I want to say, okay, so if we want to describe it as a tensor category, well, instead of just looking at this object, consider the category 0 equals all P version 3 pro P verbs. So I guess this is also, oh, sorry. So again, metrizable. So I guess this is the countable pro category of finitely generated free ability, finitely generated free is equal modules. Okay, so we can take the countable pro category or the of finitely generated free P modules. And okay, so then and let me describe the heart GFZP heart. I think that's functors. Now, I guess if we say it this way, it should be functors from C0 up to groups or sets which preserve finite products. More or less another way of saying that this object is a generator. But if you say it this way, then C0 itself is going to get a tensor structure. That's the structure that you want to define structure here. Or maybe I should.
In addition, so here you consider the product.
Yes.
Product that's on the other hand, one could consider just the definition of the count generators. This would be a smaller. This would be a smaller equipped with the periodic. Okay. Anyway, it's a smaller, at least superficially small subset. Then I could consider the endomorphisms of this. Yeah. So yeah, topology. It's true that this reality is opposite.
Yes.
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 So it's
by some
similar to
duality.
the fact that continuous and homomorphisms of
Yes, so, right, so this is, right, so I guess there's some sort of duality here. So, right, instead of the count component, we could look at the p-completed direct sum. That would be like elements of the product that are converging to zero, and we could take endomorphisms of that. Right, I guess so, okay, so I was gonna, right, I guess I was gonna say this maybe after the break. I think the idea is that in this approach, they want to take these countable products as somehow the more basic objects, rather. So this is like the unit ball in a p-adic Banach space. But they want to take these objects as the more sort of primitive and fundamental objects to build the category. Because I guess because these are profinite. So maybe now's a good time for a break. So. Okay, so right, so somehow the building blocks for this for solid ZP modules and for D of Z solid are these countable products of ZPs. But so right, so many objects that one considers are not of that form, but are more like they come more from like unit balls and in p-adic Banach spaces. So right, so another example of an object in say D of solid, but actually the heart, it's the following. So take the completed direct sum of copies of. So explicitly we could think about this as taking the direct sum, take a countable direct sum, the natural numbers of copies of integers. And that's just a discrete object. And then from the p-completion, but in like solid integers. So this gives an object, and well, it's an inverse limit as modules. Yeah, modules. So it's a or so it's in here.
yes, what you say. Naive there, I would take the show completion. Then I get it's how difficult. How does this compare with show? So the usual completion is a topological space.
Yes.
But it doesn't develop well. It's not
Profile, but it's the same construction.
but can you same construction?
Same construction. It's a metric. Yeah,
No, it's not the direct sum of focuses is not profinite either, but it's an inductive. And this thing is from the not literally but it's
So this is so well, I guess we can think about this in a couple of ways. So one is literally as written, so it's the inverse limit over n of the direct sum, let's say over I, of the direct sum and index of Z mod PPI, and just that we're forming this inverse limit in solid abelian. That's remembering, right? So the functor from abelian groups to solid abelian groups does not preserve limits. And so the limit is how taking care of the topology. We can look at it this way. If we want to define this in more topological terms, it's the space of all sequences. It's also we could define this via metric space. So consider all sequences. The set of all sequences x0, x1, x2, is ZP such that x of I 0 and give it like to the L infinity. So okay, so this is the unit it's the unit ball in a p-adic Banach space of all sequences with coefficients in p that are congruent.
Yes, but this is the last description is familiar, it looks familiar, but this is a description as a, well, as a, let's say it's topological. But is this, so are you saying that this about, so and then any topological space can be considered as condensed?
Yes.
Set, so it's just the condensed set corresponding the condensed medium corresponding to this standard, very standard Banach space.
Yes.
Okay, so this way you get an object in the heart of the category medium.
Yes.
But it's not a problem.
It's not a compact object. So this object, so this is okay, say a ZP for unit ball in a QP Banach space. So if we give it the neutral sort of metric topology, this is sort of the more algebraic categorical description, this more topological description, but this topology is also the inverse limit topology. So they are the same. So this is a topological, it's the inverse limit of if you mod out p to the n, it has a discrete topology. Okay, so this is very much not a compact object. So maybe these are objects that would arise, for example, in like the T algebra or rigid geometry, but this is very much not compact. Not compact in D of DPs. So these are sort of not taken as the building blocks, and in fact, actually, because it's very far from being profinite. However, we can give a description of this object in terms of profinite objects, in terms of profinite sets, or in terms of compact things. So, namely, so consider a function. Consider a function f from the natural numbers to, let's say, r greater than 0, positive reals. Yes, sorry, maybe. Sorry, let me not say it this way. Let me consider a function from the natural numbers to the natural numbers that tends to infinity. So let's consider a function that's ascending to infinity. So then we have so the product over, so inside this product vector is the complete direct sum of I and n of ZP. We have so we can write down some cofinite subobjects of this all in the p-adic Banach space. Namely, we'll consider the product over all I in the natural numbers of to the f of I times p. So this is one of the generating objects, the countable product of copies, and it just maps it. So for each function f from the natural number to the natural numbers that tends to infinity, we get a map from this countable product of copies of CPs into Q. So moreover, collection of all such F forms a poset, and I guess the poset it forms a poset, forms a directed poset. So I don't know. Let's call this product of Z. The directed poset. In fact, this is included. So i.e. If F is well, I guess we have to sort of index it the opposite way. So if F is less than or equal to G, then we get a map from product of G into products of F. So more slowly growing functions that grow more slowly will give you larger subobjects. And this object here is the colimit over all such functions. So so the right-hand side is the colimit of all products of F functions. So for each function that's converted, that's growing to infinity, we get a profinite subobject of this uniform in the Banach space. And as the functions grow more and more slowly, these objects get larger. And this object is the filtered colimit of all of these things. So this is how they describe these uniforms in p-adic Banach spaces in terms of the generated. It's not a count. It's not countable. This is a very large poset. So a consequence of this description is that they're able to compute tensor products of these objects. So these are maybe the objects again that might provide sort of feature. The consequence is that if you take again, let's say a completed direct sum of copies of ZP indexed, let's say over a countable set, and then take the derived tensor product, derived solid tensor product with again another countable direct sum, completed direct sum of copies of ZP. This is, well, it's again the sort of completed over direct sum. It's sort of the completed. You get the expected ends. And again, the strategy is so this over here is a colimit of these countable products over all F from I to numbers converging to infinity. They're sort of growing very slowly. And this is the same. This is a colimit over product of G over now all of G from J to the natural numbers converging to infinity. And then that writes the tensor product of these things. Well, we know how to compute the basic building blocks of these countable products of copies of these. And the tensor product of those is the expected thing. So these are colimits of the, so that expresses this tensor product. Product becomes a colimit over all F from I to the natural numbers, G from J to the natural numbers of let's say product over I comma J of let's see, P to the F of I plus G of J. And now the point is that any And the point is that these functions in the form f of I plus g of j, they're cofinal. So these give you functions from I cross j to the natural numbers that grow to infinity, and they're cofinal in the collection, in the direct implicit set of all functions from I cross j to infinity. So there's a little argument with sequences or with functions too. This is how it's proved. And actually they prove a more general fact. So a more general fact that they prove is I'll talk a little bit about there was so I did see. So they prove a general fact that a tensor product, a solid tensor product of complete things is automatically. So more generally, so given x and y, and we could say either d of z solid or d of zt solid. So it doesn't matter if the tensor product of z of c or p. Now let's say they're connected. So if x and y are p complete, then x, y, sorry, this is derived solid tensor. The tensor product has this sort of strange feature that it the tensor product of complete things remains p complete. And so actually I was sort of wondering if there was sort of a way of seeing that. So if there's some way of abstract argument using the fact that the compact objects in D of Z solid have countable properties. But in any case, this is so okay, so then a consequence. This is if you work with D of QP solid. So again, this is just going to be objects where P is invertible. So this is also a full subcategory of D of Z solid because P is idempotent. And this is compactly generated.
Just so this was
Oh, sorry, yeah. So
this is a problem that
it's a consequence. So this is by definition, I guess it's modules over QP. Modules over QP. And D of either Z or ZP solid. So this is a full subcategory of D of the full subcategory of Z solid with an object because this is an idempotent algebra. So it's just saying that it is equal to a tensor with QP. Okay, so this is also compactly generated. It's compactly generated by the object, which is a countable product of copies of CP. Then you invert P on the other side. So again, this is now an end. This is now of the sort of same form that we've encountered earlier. Namely, it's obtained by starting with a sequence of profinite sets and then taking the colimit of a sequence of profinite sets along closed functions.
So, and this is what just bounded sequences.
Yes. So the topology on bounded sequences is that again that you have some convergence if everything is uniformly bounded, and that's a sequence space. So this, I guess I call these p-adic Smith spaces because this is the dual to a bundle space. This is the dual to a bundle space.
So what's the definition of Smith space?
I think the definition of the use of a Smith space is basically it's something that so they have a definition in this context, in the context of solid QP vector spaces. So namely, it's something that has a profinite subobject. such that you get the whole thing by inverting. And so then any p-adic Smith space is a basically a Smith.
Sometimes
Solid QP vector space V. So QP module in solid groups is a Smith space if V equals V0, the join 1 over V, where V0 is profinite. That means it has to be a product, countable, finite or countable product of copies of C. So this is a condition on a solid QP.
what was the definition? What do you know the definition of space from classical situation?
So I believe that the definition.
Probably there is not sure it will
Right, yeah. So this definition also makes sense in the Archimedean context.
yes, what would be the
So I think in the Archimedean context, it would be the statement that you have a compact compact subset, and then you get everything by sort of enlarging that. So I think again the example would be something like bounded sequence. Something like all bounded sequences of real numbers.
bound sequences? But so and this would be what classical is topological vectors.
Here is a topological vector space. So I think the classical one.
What
So classical example of this space. So bounded sequences of real numbers. But the topology is such that if you restrict the bound, say be less than or equal to 1, then it's the topology. So it's not the bound, but you can also
it's
get
not the you can consider the L definitive law. And okay, so probably the classical let's say something. So consider the space L1.
Yes.
L1 is small. The better L is large. Now that consider this space is also a Barnard space, and but this is another, but there is also but I'm talking about something like topology, like big topology, a version of big topology. topology which we not found. So probably what setting?
I think the answer is that so it's not a norm, so right, so classically the analog would be, okay, so again, this is the same as here, so bounded sequences of real numbers. But topology is such that if it's so first if you look at the subspace where everything is uniformly bounded, so where the bound is uniform, you give it the product. And then it's going to be the Coleman topology on. So it's not given by the norm.
Yes. Nice feature of the edit function. Well, the nice feature of the edit function is that well, let's say all infinite dimensional space with some complete property or isomorphic to L1. But if you there are many spaces. So right? Any Barnum space. So that the space technology consider the well, consider a ball is of some range. So consider the inductor with respect to all. This construction then for instance can construct the original Barnum space.
So as far as I understand, so Smith proved that there's an anti-equivalence between Banach spaces and Smith spaces.
And did he work in the
so she worked in the Archimedean. Yes. Yes. So there's some references to this in the article, well, in the notes by Schulze on analytic geometry. So Smith showed that this is okay. So Smith showed that there's an anti-equivalence between Banach spaces and Smith spaces. So rectangular construction is essentially like this. So you start with the Banach space, then you take the collection of all the continuous linear functionals on it, and so then on the unit ball, so consider that as a Banach space. But instead of doing that, you consider, well, if you consider the functionals of, let's say, total norm at most one, you give that the I guess a weak star topology, and so then that's a compact space. It will look something like this, and then you make all functionals into a Smith space by taking this sort of covalent topology. And so the duality theorem is that this is a thing, well, that can go both ways, and it's also true in this context. So well, okay, so explicitly in this kind of setup, it's literally take internal Hom into Q. So okay, so remark. So in solid vector spaces, it's a simpler setting than non-Archimedean setting. Well, okay, so one is okay. So this is what it means to be Smith. So it's easier for the finite, and that means it's more to random copies of CPU finite countable, and we'll say that something is Banach. So we'll say that W is Banach if W equals so if W is equal to W0 if joined 1 over P, where yes, I want to say that W0 is P complete. And W0 mod P W0 is this one. So that's saying that it has the p-adic topology. So mod P is discrete. And then the duality between Smith and Banach spaces is taking internal homogeneity.
No.
Yes. Yes. Okay. So yeah, so let me just comment. So right. So what this means is that if you consider right, so if you consider a Banach space as an object of solid QP, then the tensor product is what you would sort of expect from construction on p-adic Banach spaces. There's also a result. So maybe let me just say this as an aside. So something about solid A modules. So remark is that you can also consider Fauché spaces. So you can also consider Fauché spaces. Solid Fauché spaces. These are going to be sequential inverse limits of Banach spaces. That's transition maps. And the tensor product behaves the way that you might want it to behave on Fauché spaces. The solid tensor product over QP of C behaves. So I guess this might be relevant for yeah. So for something like so example would be if you look at functions, if you look at
So Fauché it's projectable inductive.
it means projective. So for example, if you take
Countable, only countable.
yes, countable projective limits of Banach spaces. So example would be something like functions on an open unit disk, or okay. And so the statement is that the tensor product behaves well. It sort of commutes with that inverse limit, essentially. An example is that the countable product of copies of QP. What the countable product of copies of QP is countable product of copies. And this is also proved by writing these solidified. And this is also proved by writing these in terms of colimits of products of ZPs. But now you have to allow more general functions. And have to make a similar argument involving functions from n cross n to so I wanted to say something about solid A modules. So okay. So let's say A is a ring, so that's a chlorine. Last time we had the definition. So we have D of A solid by D of A. And this is going to be the objects. Such that, well, you make a similar condition. So R bond, internal R bond, over A, of A brackets hat, mod, let's say, R times hat times 1, to M is 0 for all R. So again, this defines an algorithm.
Was I a
No, for this is for any. But the condition is only, the condition is somehow one element at a time, or in fact, it only depends on any finite. So in particular, M is going to be solid as an A module if and only if it's solid over every finitely generated subring. Okay. So I think the idea is that if A over C is finitely generated, this captures the idea, or this is analogous to so complete with respect okay, so in particular, this such an object is solid as an abelian group, but in fact so in particular it's solid as an abelian group and it's an A module, but it's somehow more than that. It's analogous to complete with respect to an A linear determinant. So it has a neighborhood basis consisting of A modules. And then the theorem. So the theorem is that if A is finitely generated over C. Okay, so this is always going to be a compactly generated category. So if A, and it's going to be compactly generated by the solidification of A tensor C double brackets T. But if A over C is finitely generated, okay, so then the statement is that okay, so D of A solid is compactly generated by a countable product of copies of it. So in particular, right, so in particular, how would you get, so if you were just working with A modules in solid abelian groups, you would start with the compact generator, A tensor countable product of copies of C. And the statement is that if you solidify that as an A module, you get the countable product of copies of C. Okay. So yeah, so I guess so again, the idea is that this is something that's solid A modules or D of A solid. Yes.
Just define the thing as in the category of A.
Yeah. Yes. So yeah, so I should Okay, so again, this is going to be an analytic ring by sort of this general theory, but then one has to compute the objects, and the claim is that these are the objects. So if A is not finitely generated, then you can describe, then basically it's a filter colimit. The filter colimit of what you'll get is the filter colimit of the categories of A modules where A is finitely generated. Okay. So great. So I guess I thought I could explain this for so example, maybe let's prove this when A is a polynomial ring. So right, so what we need to show great, so I think it's formal once one has the solid ability proofs. It's formal that this object is a compact gem. So you really just, the main thing is just to compute this, the solidification, the drug solidification of this. So we need to show that so C brackets X tensor the countable product of copies of C mapping to countable product of C brackets X. Then this map induces an equivalence on A solidification. Okay, so right, so the idea is well, the idea is to consider an object in this context that played the role of the real numbers in setting up the solid Z. So in particular, in setting up solid Z, it was important that you have the real numbers, which was an object whose solidification was 0, because you had this element 1/2, which was, yeah. So the analog of the real numbers is the object. So Z, so it's this object, Z Laurent series X inverse. So by definition, we take the power series ring in Z double brackets, the power series ring in the element 1 over X. Okay, so that doesn't receive a map of the equation 1 over X. But then we invert X, or we invert X inverse. So this is an example. This is an example of something whose derived solidification is going to be 0. So this is a module. So this has a map from. So this is a module over, so Z brackets X comma Q hat. So there's a map from Z brackets. So in this ring, 1 over X is logically nilpotent. So this receives a map from Z brackets X comma Q hat on X Q hat. So this is exactly how the real numbers receive the map from Z brackets hat on 2 times Q hat. So it's a module over this object, and that means that its solidification by construction, its solidification as a brackets X module is 0. So in Z brackets X, solidification is 0. Okay, so now we're going to do the same thing as with the real numbers. So let's go back to this board. And right. So okay, so the claim is that there's going to be a Cartesian square where you have Z Laurent series X inverse tensor product over n with Z mapping to the product over n with Z Laurent series X inverse. The claim is that this square that you get is bicartesian. So this was the analog of what happened for Z. So the claim is that this square is bicartesian. And okay, so if this is bicartesian, then we're done, because the difference between these two is then something that's going to vanish upon Z brackets X solidification. So why is it bicartesian? So by the way, I should say that all the products are going to be in solid abelian groups. So I'm going to do everything in solid abelian groups. Okay, so the point is that the difference between these two, so see that it's bicartesian, see that the square is bicartesian. Well, I think both maps are going to be injected. So to see that it's bicartesian, both the vertical maps are injected. So we need to see the map on vertical cokernels. In isomorphism. But what is that map? That map is the map Z. Well, so if we just consider it, so again, we just have to consider it in solid abelian groups, and it's the map Z double brackets X inverse. Well, X inverse. So it's going to be all power series. So it's this map. Insert integral product mapping to the integral product of, again, so it's Z Laurent series X inverse mod Z brackets X, which is X, well, just 1 over X times Z double brackets X. But just, I mean, this is an isomorphism of solid abelian groups, because this is a problem of copies of Z, tensor of copies of Z. So we got to do copies of Z. So this, so the solid abelian groups. Okay, so I guess that's the proof. Well, okay, so really that's a proof that this map induces an equivalence on Z brackets X solidifications. But I guess it's straightforward to see that Z brackets X itself is solid as a Z brackets X module. So is any. So, okay, so that's the proof. Well, so that's a proof for Z brackets X. And well, maybe I should just mark. So in general, okay, so in general, one sort of reduces to this case. But in fact, one can show that if you have an A module, so if A is an algebra, which has a bunch of generators as an algebra, then to be solid as an A module is the same as being solid over each of those generators. So as you look at the solid over Z brackets X, where X maps to each of those generators. So I guess I'm out of time, but I guess one thing to point out is that this distinction between solid A modules and A modules in solid abelian groups turns out to be sort of, well, one is that it gives you some flexibility that one didn't have in ordinary, like ordinary algebraic geometry. So sort of have different sort of objects that you can consider. And so a consequence of this in the original condensed.pdf notes is that they're able to give a new proof of, well, so they're able to give a very nice proof of the fact that if you have a catalyst, let's say you have a Hopper's equal to integers, then the cohomology of any coherent sheaf is finite dimensional over Z. And the proof is really based on the value type criterion for properness, and using the fact that you have these two notions of solid, so and sort of playing off using the fact that you get these two notions of solid A modules versus A modules and solid ability.
Is it sort of a, well, yeah, the logic is similar to proof that complex geometry would prove that the knowledge of coherent shapes are finitely much manipulating, taking line covering, those line coverings which one that's into another this this property. Well, section closures sequences open and considering
Yes.
this type of argument.
I believe that was part of the inspiration. So maybe just to say very quickly, the idea is that like if you want to show that the cohomology of something on, or we just say something on P1 is finite dimensional, well, the idea is that you use these two coverings. One is the covering of P1 by two copies of the affine line, and thinking about like Z brackets X modules and Z brackets X inverse modules. But the other is to use sort of the cover, or like an analytic covering of P1, where you work with solid Z brackets X modules, solid Z brackets X modules. And well, one of those will give you this fineness directly, and the point is that both of those coverings give you the same theory of possible issues. So they also have some, they also have an approach to like formal Gaga in this context. Anyway, so I guess it is 6:30. So, well, maybe if there are questions or comments.